All right, class. I'm going to go back through the tutorial that we started in class the other day, trying to just reinforce some of the things we were doing with the graphic standards diagram about sight lines, and trying to test to make sure each of the seats works using a Grasshopper script. I'm going to go pretty fast through this first part because I feel like you already took care of it. If this didn't make sense to you, I hope that you'll go back through, or you need to go back through this video and make sure that everything is coming back in terms of Grasshopper. So again, we're just going to start by using a couple of curve components and a couple of area components, and I like to just go ahead and set these up and then copy and paste them to make it a little bit faster. Again, in each instance, I'm just double clicking in the gray area here to create almost any component inside of Grasshopper. Select the curve, set one curve for the front, select the one in the back, set one curve. I'm just going to lock the layer that the plan drawing is on here in the default layer, so that things don't keep moving on me. And I'll jump into perspective. There's a point here in mind, but you can also use the curve that's on top of the stage to find the centroid of the stage. I'll set one curve there. If you want, you can change the name of these to try to keep yourself organized. So all I did was right click on it, and I'm here in the top changing the name. So this is stage curve, and then if I want to use the area component here, I could change the name of the area to stage centroid. That's what I'm using it for. So in this instance, if you're having any issues staying organized, this is the easiest way to make sense of all that. So I'm just going to change these to front seat curve as well. So the important part of the calculation here was the distance between these two centroids divided by 10. Put a division component in and divided by 10. And then we're moving the front seat. Excuse me, we're moving the front seat. I'm going to use the curve in this case, not the centroid. And we're going to move it in the Z direction. And again, it was the 44 inches. And I'm just going to use an addition component to add this value, which is I'm going to change to L divided by 10 so that it makes sense. And if you want, this is distance between seats. And again, in that diagram, this diagram here, we're taking the height from the floor up to the sight line for the person in the front row, adding L over 10, L being the distance horizontally between the front row and the back row. It's not that complicated, people, so we're trying to get this seat moved up to the height X, again, to find this slope between the two seats to maintain a sight line. So here's that L over 10. I'm going to add 44, which is the height of the person in the front row. And then that is the distance we're going to move that first seat up in space. You can see it over here. And then we can again take the centroid of that seat and draw a line. And again, when I double click here and I type in some of these components, you're going to always see these black ones that appear in the bottom row. Those are just containers, and you can see this one actually has a spelling error in the name. Contains a collection of line segments. Those are just simply containers. They hold real geometry inside of Rhino. Anytime you see that black hexagon, that's what's going on there. So don't fret. So we're drawing a line from the center of the stage to the center of my newly elevated seat, and then we're going to use that curve extend component to extend this to the back of the theater. Again, you need a 0. That's how far we're extending L0. If I mouse over it, it says extension length at start of curve. We don't want to extend it further into the stage or into the theater. We want to extend it towards the back to find that intersection. I'm just going to put a big value here on this component. It looks like mine is flipped. So I'm just going to, for the sake of efficiency, flip the centroid so that it's in the B and my curve goes to the back of the theater. And then again, I'm going to draw a line using an SDL. Line SDL, start, distance, and length from the rear seat. Centroid is the start. Big value for the length. All we're trying to do is find the intersection of these two components, and the direction is in the Z. Again, this is a component that's very useful when you're trying to draw a line when you only have a start point and you don't have an end point. The curve intersect component is going to allow us to find the point where these two things intersect here in the back of the theater. There's our point. We're also going to need, as we were describing at the end, a vector 2 point in order to actually figure out what the direction is of this slope as we go to move these seats around. I think I mentioned this at some point, but this seat in the back seems to have gotten moved, so I'm just going to use a move vertical to set it back to 0. Make sure everything else is right here. I think we're okay. Okay, so the vector 2 point we're going to use from the stage centroid to our new intersection point at the back. So vector 2 point is just creating a vector that goes from here back to here. This is representing the angle of the slope of the seats, and we're going to need that in order to use the linear array to array the seats through the space. This vector can be visualized using a vector display component right here. You can see this doesn't have any outputs because there's nothing you can use it for. If I get it put in here, sorry, it needs an anchor point, which will be that centroid at the stage. That way we know where it starts. And you can see this kind of feathered end just indicates that the vector can't be used anywhere. You have to use the non-visible one that's here in the vector 2 point component. But you can see the little arrowhead indicating the length, which is the force, not geometry, but the force of the vector. Moving through the theater. Okay, now we're going to use a move component to move that front seat. Excuse me, we're not going to use a move component. We're going to use an array component, linear array component, to move that seat, the front seat. And take the actual curve from the front seat, and we're going to move it along this vector. But we do need to divide that vector. You can see the length of this vector. Each seat in the linear array is going to move that whole big distance. So we need to, again, we can use multiplication and division in order to change the length of a vector. So in this case, I'm going to divide it by 19 just to start off with, because that's roughly the number of, or that is the number of rows that are in the theater. That's also the number of rows that we're going to position here. You can see once I get the divided vector in and the appropriate count of seats, you can see them actually moving through the space. I'm going to look in the top view and see that I need to adjust the vector a little bit until I get that last seat bit roughly where I want it. Looks like around 22. I right click on the slider and change it to a floating point slider. I can get a little bit more precision if I change the max value down to like 25. This also will give me the kind of control that I want. It's going to work for me. You can see it gets a little bit off here because of the gap here in the front row. I'm not too concerned with that. You can, you presumably are going to have more consistent kind of control over your own theater design. So once we've got this linear array, now we're going to do a polar array in order to actually do the rows through the theater. Again, the geometry coming out of each of these rows. You can see I get these kind of fantastic patterns at first. Again, the array is going to be relatively, or the degrees in the array are going to be relatively small. So I'm going to start off just by putting the angle in at about 7 degrees. If you right click on the polar array, you can change it so that it's in degrees. And now we're seeing roughly how many, we're seeing roughly the number of arrayed seats that we need. We're going to have to do this twice in order to get it offset. And we're also going to want to alternate the number of seats in each row so that it's offset a little bit. So it looks like there's 1, 2, 3. Looks like about 10 in that front row. So I'm going to start off just so that this makes sense by putting 10 in on that side. And then again, this P for plane is the actual intersection point of the giant piece of pie that is this polar array. So this is the centroid that everything's rotating around. The easiest way to get that is to use a move. And if you look here in the plan drawing, you can see that the Y direction is along the axis, the center axis of our theater. So I'm going to put a Y component in. And we're going to start with the centroid of this front seat. I'll move this setup over here. And I'm going to put a big slider, something like 10,000 into the Y, and use that as the centroid for my seats. And you can see as I reduce this, it's going to pull those seats into alignment inside of the theater. And of course you can again come in and edit this. I'm going to edit it so the max is 2500. That's going to give me more control. You know, don't worry about the fact that there's extra seats back here. You'd rather have extras than too few. You can always go in and delete them. And what's happening here is the point is way back here. And actually, you know, this looks pretty fitting for Foster to have continued the axis of the theater back to the back of the building and used it as an organization. And also that the seat array would have some kind of a geometric element to it that relates to the rest of the building. So not surprising that it's at the crux of this corridor in the back of the building. We're going to copy and paste this component, and I'm just going to right click. If ever you want to turn something negative, the simplest way to do that in Grasshopper is to right click on the component that you want to flip to negative. Go to the expression. The only time you're ever going to use the expression in all reality, and put in -x. It's just simply saying whatever variable is going in here, make it negative. So I will put that on the degrees, and you can see that that gives me the array in the other direction, the polar array in the other direction for the seats. If I want to, I can change this so that I have an alternating number of seats in each row, or I could shift the seats so that I can alternate the head height. But the point here is not necessarily to array the seats. I'm hoping that you'll organize your own seats in your own theater the way that you see fit, but really instead to figure out how to set the elevations, and then to test the sight lines from those heights. So now that we have all of these seats, we can put them into the same list. Now is the test part. So I'm going to make a curve container. Hold shift to put all of the seats into the same curve container. So we're treating them exactly the same. And now again, the final component of this is to use a BREP curve intersect. So a BREP, for those of you that don't remember, a BREP is any kind of solid geometry. It actually could be a surface or a solid. It really can be almost anything inside a Grasshopper. BREP stands for boundary representation. The key thing to just remember there is, like, it's a container that can take almost anything. You can see when I type the word BREP in, there are a ton of options. We're eventually trying to get to this BREP line intersect, where we're going to intersect sight lines with seats and seat heights. So our seats are all sitting presumably on the floor right now. And so what we want to do is extrude those seats. I'm going to use an extrude component. You can see the extrude is very simple. It wants a base curve and then an extrusion direction. Again, a vector. So I'm going to put a Z in with that. The height of a person, which we're going to call 48 inches for the sake of this argument. If you look at it in graphic standards and the other drawing that I attached, it's a little bit higher, but that's presuming, I think, bigger, some bigger seats. So those are going to be the heads that are going to occlude our view. And then the lines need to go from the centroids, so again, another area component of all the seats in the theater, so I'm trying to make a line component. So from these centroids back to the center of the theater, center of the stage. So I'm going to come back here, find that centroid. There are all of our sight lines, and those are the intersections we're going to test for. I'm getting 380 issues right now. So the point here isn't to solve all of the issues, but instead to find them. So when I select this, you can see, should be able to put a point component in, and that's going to allow me to find it looks like basically every seat is getting hit. Well, that doesn't make sense. Oh, all right. Hang on a second. These curves are down at the seats. We don't want to test from the centroid of that. We want to move those up to the sight line, which was at 44 inches. All right, that would explain our problem. So we're going to move this Z again. This time only 44. Okay, so what's happening here? We're extruding the seats up to the height of people's heads. That's in the Z direction, 48 inches. That's the top of my head. Here, the sight lines, we want to extrude up to the height of people's eyes, which is the 44-inch component. That's where we need to get the centroid from to create the sight lines. And now you can see that our where those sight lines are, and hopefully we don't, we still have some intersections. There you can see where the intersection problems are occurring. It looks like right in the head in front of people, which makes perfect sense because we haven't offset any of these seats, which is the next step that you need to do in order to make your theater successful. So there you go. You can use this, and if you want to adjust what the extrusion looks like, you could do it as a cylinder. You could do it as a pipe so that so that people's heads are a little bit smaller. So if you wanted to do that, you would just take an area component again to get those centroids, and then you could do a cylinder, which is going to require a base plane, a radius, and a length. So the base plane is the centroid of that area. Presumably somebody's head is, let's go with 5 inches for the radius, And the length of that is going to be our 48. So if I turn the preview off, I'm going to right click on the extrusion and see those cylinders now. Maybe a little bit more appropriate. Put that into the intersection, and we're still hitting everybody's heads with our view. So the key aspect here, it seems like, isn't necessarily the size of people's heads. It's really about getting the offsets between each of the seats so that you're not occluding people's views straight back along that diagonal. So really we need to shift every other row to have 9 or 10 seats inside of it. Okay, so go back through this if any of it didn't make sense. There isn't anything that crazy. We're definitely going to get a lot crazier with stuff tomorrow. So please take a chance to go back through this and refresh yourself. The ins and outs of Grasshopper. Okay, see you tomorrow.